make your grand entrance.
How do I look?
Perfect. Absolutely.
Opinions vary.
Do you remember Alan Ladd and Shane? Okay, now do your thing.
I don't remember.
Use your drum roll first.
Who's Alan Ladd? What's his name? Is that something from?
It's before our time. Okay.
7 minutes after 6. Not one single person. Oh, Reggie wanted to know. Okay, last time that I taught, which was it's probably been 3 weeks now. Last time I taught, we talked about pre-treatment and we got through electropolish. So I just want to real quick finish up the pre-treatment section and then go through the beginning of some calculations. And after this class, the people that have not had SPC are going to start SPC training for the next 10 weeks. So then I won't be resuming until whatever that is, end of March or something. Yeah, end of March. Okay. Acid activation is the final step before we do any kind of plating, whether it be nickel plating or whether we skip and go on and do gold plating or tin lead plating. There's two main purposes for having acid activation. One is when you come out of position 12 here, which is a caustic cleaner. And there's a rinse in between here, but then you have your acid activation. Has anyone ever gotten some of this caustic cleaning solution on their hands? Yeah. Tried to go in here. You've got a rinse, right? You got a water rinse. If you go get that soap on your hands, and you go over to the water faucet and put your hands under there and start wiping it, you're going to be there for about 30 seconds trying to get it off. You feel it and feel it and feel it. And when we're going out of here and pass through this rinse at 10 meters a minute, we're probably in there for a couple seconds, a second maybe. So this rinse is not going to get this off the part. The acid will neutralize the caustic. So that's one thing that's happening. If you remember from before, 7, this is neutral, and a pH of more than 7 is caustic, or also sometimes it's called basic, or also alkaline. And less than 7 is acid. So this pH here is about 1, and this pH here is about 12. Okay, so those get together, they neutralize each other, and it makes it real easy for the caustic to come off of the part, to rinse off. Because if that slime is on there to go into your plating cell, you're not going to plate. There'll be a film in between your metal and what you're trying to plate onto there. You won't get into plating. The other thing is it's the last, what you're doing in your cleaners primarily is getting the oil off. And here what you're doing is you're actually getting rid of some of the oxides or some of the non-organic type of surface contaminant. Your organic type, which is the oils and the machine stamping oils, are coming off here, caustic cleaner. That's basically what you're doing here. Usually we have, I would say, 99% of what we do is sulfuric acid. Okay? Everybody, well, I don't know if everybody does know that, but that's what's in position 14, which is in the final acid activator. Sulfuric acid is about a 10% solution of sulfuric acid in water. The other 1% is split up every once in a while. We use hydrochloric. Okay? And sometimes also, this is a little bit more common, we'll use sulfuric, but with current. Okay? This is 99% sulfuric acid dip with no current. So that's the three. I just want to talk about it a little bit. That's the really, I don't think there's any other activation we do besides those three. Just a note, I don't think this is in there, but sulfuric, sometimes you see this right here. This is the chemical symbol for sulfuric acid and hydrochloric. Is this HCl. Sometimes you hear people say HCl, and that's what they're talking about, hydrochloric acid. Okay, why do we use this 99% of the time? Okay, the hydrochloric acid has got this in it, chlorine, in which chlorine attacks steels, any kind of steel, including stainless steel. Eventually we get attacked by this. And so it's real rough on the equipment. So we prefer not to use it at all, but sometimes it's, for some raw materials, it's a more aggressive activator. So sometimes we have to use it. The sulfuric acid usually does a job for most everything we do, and it doesn't have the same effect on the equipment. Okay? Now sometimes we're using sulfuric acid with current. Okay? When we do that is when we've got a product that's relatively difficult to activate. And most of the times, what we'll do, this is your cell here. Most of the times we wire it cathodically, right? Which means it's wired the same way that a plating cell would be wired. When we wire it like this, first of all, there's no metals in this solution. So there's no plating going on. So this is what we talked about last time when we talked about caustic cleaners. When you're trying to plate, you're pushing current through the cell, and there's no metals. What you end up doing is you end up making this gas here that you see bubbling off the part, and that's hydrogen. Hydrogen gas, which is a nice gas to have there at the surface of the part. Plus you get the scrubbing action. This usually makes the cleaning more effective, but most times for what we're doing, we don't need it. So it just adds another step. It adds a rectifier, and sometimes adds a contact. So if you don't need it, why use it? Also, there are also times, and you have to look real carefully. There's actually only one in the plant now, where we use anodic sulfuric. Okay, so you hook the positive up here and the negative up here. That's anodic. We use this for Genum, LTI Genum. But you don't have to remember that. All you have to remember is when you go to set up a line, look at the EDS, because not too long ago, maybe 6 months ago, somebody went, set up LTI Genum, and we had a very minor peeling problem on the first half of the run. Then we went out there and checked, and it was wired backwards. It was wired cathodic. It's clearly written on the EDS wired anode. So basically, that's all that in this plant. That's all we do in that position 14. And these more severe types, like this anodic, and also cathodic cleaning with sulfuric, or also hydrochloric, are usually done when you're trying to plate on a stainless steel. It's very difficult to get the sulfamate nickel to stick on a stainless steel unless you really active it. Okay, I want to talk about strike baths, strikes. Okay. Why do we even have strike baths? There's a main principal reason for having a strike.
To ensure good adhesion for the primary plate.
Exactly. It's exactly what you're doing. The strike, the reason we're striking it is for adhesion. There are some other purposes for it that it serves. Sometimes people say it helps with porosity, but we're not really sure about that. That's not what we're doing it for. We're doing it because it makes the real heavy plate stick better. This bath is designed to stick. It's not designed to plate fast. So there's a couple basic things about a strike bath that usually apply, not always, but usually. Usually it's low metals, okay, low efficiency, low pH, okay. Low pH makes it a very acid thing, so it makes the solution itself very active. Low efficiency, again, when you have low efficiency plating, efficiency, just so we all really know what this means, and we all say a percent, well, you know, what's the efficiency? Well, it's 50%, or I have a poor efficiency. People use this word. What it means is it's the percent of the current that's actually being used to plate. Okay? We all know, well, we don't all know, but with gold plating, for instance, you might be running 2 amps on a product with a very small surface area, and you might have 30 microinches. You can double amps to 4 amps, and you still have 30 microinches. I mean, you know you're putting 4 amps through the cell, but yet, you know you've doubled the current, but yet there's no more plating thickness. That's because the efficiency is low, because only a small percentage of the current is being used to plate. When the efficiency is low, what the result is that, again, you're generating this hydrogen. Because it's either one or the other is what you're going to do. Either you're going to plate, or you're going to generate hydrogen. That's why, like in a controlled depth tin lead cell, sometimes you see it a lot. You start adjusting the current, and if it goes too high, you start seeing the gassing. That's when your efficiency is going to start to drop off. Because now you're using your current from your rectifier to make hydrogen gas instead of to plate metals out. In this case, in a strike bath, that's what you want. You want it to stick. You don't want to make any thickness. You don't care about that. Same thing here. Low metals makes it usually not efficient. Okay? Now, let's talk about the specific types of strike baths that we use. We use nickel. Let's talk about nickel first. Nickel strikes usually used on, usually the reason to use them is because of the raw material. We don't use them that often, but when we do use them, it's usually because the raw material is a stainless steel, or it's some kind of what we call a ferrous alloy. Okay? Ferrous alloys, and where that word comes from is this symbol right here, Fe, is a chemical symbol for iron. Okay? Just like Pb is for lead. Okay? That means an alloy that primarily contains iron, which is like steel or stainless steel. And those types of materials tend to be difficult to activate. And you end up having a lot of problems trying to stick your nickel plate onto it. And matter of fact, if we look right now at the applications we have in this plant where we're using nickel strike, that's what they are. They're LTI Genum, which is nickel iron, and they're AMP stainless steel, which is stainless steel, which is mostly iron. And that's really the two that we have. Okay. We have two types we use. We use a Watts, which is a sulfate type bath. We have a Woods, which is a chloride type. This is the same situation as, remember we talked about sulfuric acid and hydrochloric acid. This was sulfuric acid, this is hydrochloric acid. We don't like this guy. That's why you really don't see this one. We don't use this one too much. Matter of fact, right now the only thing we use it on is Burndy, which we don't really even run. This is one we use by choice in activating a stainless steel. This one has a very low pH. pH is about 1. By comparison, pH of the plating bath, of the nickel sulfamate bath, is about 4. pH is 4. You see it's much lower. It makes it very inefficient. So you're not going to get much thickness out of this, but it's going to stick to anything. Now once you put this nickel strike on, now you've got a nice clean deposit of nickel. Now you can go ahead and put all your regular nickel thickness on top of it. Okay, so there's 2 types. And these, it's not only used as a preplate for nickel, it's also used as a preplate for gold or a preplate for tin lead. Other type of strike we use is one we use on just about everything, which is your gold strike. It's the same strike, we use it on just about every product we run if we plate gold on it. Mainly here what you have is, the pH isn't really low, but the metals are very low. Metals, again, it's a good example of how a strike bath is low in efficiency, low in metals, has about 1 gram per liter. Plate bath has about 12. Okay. Also the temperature here, room 60. Both of these things make this bath very inefficient. You can't get any thickness at all out of it. And this is the opposite here. Okay. Okay, one other item I just wanted to briefly mention is ultrasonic cleaning. We don't use it in the plant, but just want to briefly talk about it because people mention it. Basically what it is it's a way to get a very severe agitation at the surface of the part. And it's usually used with a caustic cleaner, like at the very, very beginning of the line, for running very high speeds and when you're trying to clean off maybe a real bad oil problem. A lot of people say it works very well. A lot of people really swear by it. The reason we don't use it is the price. It goes for a unit about this long. It's a little tube and your product passes through it and you have a generator up here that generates these sonic waves and somehow it causes agitation of the solution right at the part. But the cost of one unit is on the order of $25,000 for a unit of this long, a little tube you put in the front of your line. And our cleaning seems to be good enough that we haven't needed it. Okay, I'm finished with that section, and what happened is when we had that pre-plating section, I couldn't get it all in the last class, so now we're finished with that. Now I want to go on, unless there's any questions, I want to go on with line speed, and plating thickness calculations. Okay, we all know, shouldn't keep saying it, but most of us know that the line speed affects thickness. Okay, But we're going to talk about how to calculate this effect, but we're going to go into a lot of detail on how this equation that we use to calculate line speeds and what's going to happen to plating thickness. We're going to talk about how that equation comes about. And basically what's happening is when you change line speed, you're changing the length of time that the product stays in the plating solution. Okay? So we're going to go through an example here. Hopefully try to explain how it is that line speed has this effect on plating thickness. And it's pretty common sense, but sometimes it helps you go through this exercise. If you have a plating cell here, and the cell can be a controlled depth cell, it can be a wheel unit, it can be any type of plating cell. And let's say that plating cell has a length of 2 meters. And let's say the speed is 10 meters per minute. And when I say, I want to go back, when I say 2 meters, I mean effective cell length. Okay? And what do I mean when I say effective cell length? That means the length where the product is actually in the plating solution. You can't count the area between the cell wall and the product gate where it's in the air. That doesn't count. Only where it's in the solution and it sees the current. Okay? So if I have this situation and I take a little strip of material here and I mark it, and then I want to know how long is that little strip of material going to stay exposed to the plating solution? How much time does it stay in there? And that time we call by a bunch of different names: residence time, retention time, dwell time. It's the time that the particular portion of the product remains exposed to whatever the process is. Okay? In any case, all of those are the same thing, and what they are equal to is they're equal to the length divided by speed. It's the same way as if you're driving home and you want to know how long does it take me to get home. Well, it's however far it is divided by how fast you drive. Okay, so in this case here, that's 2 meters divided by 10 meters per minute. And that equals 0.2 minutes. Okay? Now, if we, in order to change the line speed, or in order to change the thickness by changing the line speed, what we're effectively doing is we're changing the amount of time that that product stays in the cell. Okay, so let's say that we wanted to okay, I'm going to go by the same example here. Let's say that we have a product with a plating thickness of 80 microinches. Okay? Thickness is 80. What happens to that thickness when we increase the dwell time from 0.2, which is what we just calculated, up to 0.25? Well, we know the longer it's in there, the longer the product's in there, the more thickness you're going to have. What you end up doing is you end up dividing those dwell times. You end up dividing one dwell time by another dwell time, times it by your thickness that you have now, and that gives you your new thickness. So, if we stay in there, instead of 0.2 minutes, if we're staying there for 0.25 minutes, which is longer, the thickness that was 80 microinches will go up to 100 microinches. Okay? if, okay, let's say that we were doing this calculation, we said, okay, that's what I want to do. I want to increase the thickness from 80 to 100. And I know to do that I have to increase the dwell time from 0.2 to 0.25. Okay, how do I increase the dwell time from 0.2 to 0.25? Well, remember this, the dwell time is the length of the cell, effective length, divided by speed. Okay? Now I want to change this dwell time. But this here I can't change. I can't change the length of the cell because it's fixed in the machine, it's fixed in the wheel unit or the spot unit or whatever it is. I can't make it longer or shorter. So this is the only thing I can do to change it. Okay? So let's say, okay, I want to adjust my, so now we have to adjust the speed to change its thickness. Okay? But we have to adjust the speed to change the dwell time. So we got the two dwell times. Let's say we're running 10 meters per minute now. And we want to change the dwell time from 2 to 2.5. Again, we have to multiply by this ratio. Okay? What this is saying is that to change the dwell time from 2 to 2.5, I have to change the speed from 10 to 8, which makes sense. I mean, you got to slow down to increase the amount of time that this is in the solution. Okay? When we do these line speed thickness calculations out on the floor, we never even talk about this. Matter of fact, a lot of you, this is probably the first time you've ever even heard of this before. But the reason I went through this is so we understand what we're really doing. There's something happening back in there. We're just punching some numbers on a calculator, but that's what we're really doing. We're calculating how we're going to change the amount of time this is in there. Because the longer it's in there, the more it's going to play. To actually, and I wouldn't want anyone to go through this on the floor, because it just takes too long. What we ended up with was we said we have to go from 10 meters a minute to 8 meters a minute to get the thickness to go from 80 to 100 microinches. That's what we ended up with after we went through all that rigmarole. But what we're going to do, when we want to know what line speed we have to change, or how we have to adjust the line speed to get the thickness that we want, if you have a thickness you want and a thickness that you have, you take the thickness that you have. We're going to use a different example. Let's say, use this one I got here, 4, 5, and 75. Let's say we're running, let's see, how do I want to do this? I don't want to do it exactly the same way we got it here, so we follow along with it. Okay, here's what we're going to do. Let's say that we know we have a thickness of 75 microinches. Okay, thickness of 75 microinches. Now, for whatever reason, we know we're going to increase our line speed from 4 to 5. Let's say that for some reason we had some other thickness and we said, okay, I can go to 5 meters a minute. But I want to know what's going to happen to the 75 microinches when I speed the line up. First of all, you just have to realize and just think for just a second, and everybody probably knows this, when you speed the line up, the thickness is going to go down. I know that's obvious, but just remember that, because this is the thickness that you have, and you want to know over here, you want to know what is the thickness going to be. You have to divide these speeds by one another. But which one do you divide into the other one? Well, rather than trying to remember, is it the old speed or the new speed, or you don't even have to worry about it. All you have to know is, well, I know the thickness is going to go down because I'm speeding up. So just multiply by 4 divided by 5. And then that'll give you a smaller number. That equals 60. If you get this backwards and you say, okay, I have 75 microinches, I speed the line up from 4 to 5, and you say, okay, what's my thickness going to be? And let's say you went through and you did this. Well, you're going to get, I don't know what it is, it's going to be about 93 or something like that. That won't make any sense. You're going to say, wait a minute, I'm going to speed the line up and my thickness is going to go from 75 to 93, I must have done something wrong. The main thing you have to remember is take whatever thickness you've got and multiply it by the ratio of the speeds. Divide one speed into the other speed and multiply it by the thickness. This is the less common of the two types of calculations that we can do. Usually what we do is more like this. We have a thickness. Okay? We want another thickness. Okay? We have a speed over here. And what we want to know is what speed do we need to do? What speed do we need to have to get this thickness here? If we have this information, we want to know how fast should this line run in order to get this thickness up from 30 to 40 microinches. Okay, so it's the same thing as when you've got a plating thickness calculation. You take the speed that you've got, and you're going to multiply it by these two thicknesses divided into each other. But first, before you divide them, you say, okay, I want to take my thickness from 30 to 40. So I'm going to have to slow down. Because I have to slow the line down so I can increase the amount of time I'm in here. Okay? So that means we should make it like this. And that should give us 3 meters per minute. Hopefully we don't run anything in this plant at 3 meters per minute, but so you're basically taking the thing that you want to know, which is the speed. You're taking, okay, here's my speed I've got now, and I'm going to multiply it by these two thicknesses. If you want to know what thickness you're going to get, you take the thickness you have now and multiply it by one speed over the other speed. Okay? But the key to all this is as far as why does an adjustment in line speed give you a different plating thickness? Is because an adjustment in line speed gives you a different retention time or a different residence time. Well, that was quick, but that's the class for tonight. So unless there's any questions, you guys.
You could go in and do some advanced algebra.
It's like a rock. Some fellow did fit himself.
I mean, we made this company $3 million in the last few months, and all they can give us is an apple.
Hell yeah.
Go for it, Doug.
Yeah, man. Let's go. This is what we're going to do. We're going to finish up the pre-plating, pre-treatment operations. Go through just a little bit of calculations.
Have you got any more of these sheets you handed out?
I'll share with you. Yeah, no, I got it. Sign the other sheet.
I'm sorry I delayed your class. Tried.
That's all right. He probably went by the Pizza Hut. He probably went by and told him.
Yeah, I better not find out.
That sounds like some shit he'd do. He did some shit like this today.
Oh, yeah. Okay, we got to the end of the electropolish section. So, we're talking about acid activation, which is the last step that we usually do before nickel plate. Okay. So you got position 12 here, which is a caustic. And then we got a rinse. And here we have position 14, which is our acid activator. And what's the purpose of this position?
Take off any copper or anything else after it's clean.
It's taking you down to your final clean layer of material that you're going to put your plate on. Taking maybe the last bits of oxide off. But there's another reason for having this here. Just remember this one. This is caustic. Just remember, it's a high pH. It's a pH of about 12. This is a pH of about 1. So one other thing's happening here besides you remove the oxide. If anyone's ever gotten this solution on their hands, solution here, and then you go over to the sink to try to rinse it off, it doesn't rinse off. You rinse it, and rinse it, and rinse it, and rinse it. Now, if we just took our material, went through here, and then went through this rinse where it's in there only for a second, you think that rinse is going to take that off of there? No, it won't. It'll just take just sort of the bulk of it off. But what happens is you get into here, and that slime, that film you feel in your hands, it's also on the bar here, then gets neutralized here. Because remember, we talked about this before. You got a high pH here, you got a low pH here. Those two get together and they neutralize one another. Okay, so you get rid of that film, so when you go in there you don't have any film. You want a squeaky, clean, copper, well most of the time copper, sometimes steel, but a squeaky clean substrate, which is the raw material to plate on. Okay? Now we use probably 99% of what we do is an acid dip, which is no current, and what we use is sulfuric acid. Okay? Which is about a 10% solution of sulfuric acid in water. That's what the solution is in 14. This is a chemical symbol for it. Okay, so sometimes you might see that around, you might see that on a container. This is a chemical symbol for sulfuric acid. The other 1% of the time, we'll use a cathodic or anodic sulfuric or a hydrochloric. Now, and this one is HCl. Now, why do we want to use this so much more than we want to use this? Because this actually is a pretty good activator. It's a strong activator. The gas, you get that fume. But what this does is when you get this chlorine, that is a bad guy to have around. Anything containing iron, which is any kind of steel. Any kind of structural steel in the roof, steel that holds up the plating channel, and includes stainless steel. It'll eventually make it corrode, rust, pit, so we don't like it. Plus it's nasty. It's a nasty
Well, he's up a
smell.
pump motor out there sometimes.
It will. It'll anything that's got steel in it will corrode.
Just the evaporation into
Yeah.
the atmosphere of the structure in the building.
If you look up in the building, I'm pretty sure you look up there and you see that painted, you'll see the rust, and this will cause that. We've used it here. Probably that's one of the main causes why it's rusting up there. So we don't really like to use it, and I don't really know of anything right now that we haven't specified on. The cathodic and the anodic is basically when you have something that needs a little bit more of a boost on activation. The reason we don't normally use it is because we don't need it, and it just adds another step. It adds a rectifier and a contact. Maybe not necessarily a contact. You can use the one at 15, but it adds another variable that we don't need. When you clean cathodically, if you remember from last time, there's no metals in here, or relatively almost none. So basically all you're doing, once again, you have your anode here, your cathode here, is you're making, we talked about last time, we're making this hydrogen gas here. It's the same thing that happens over here. Okay, so it helps agitate it, and plus this is a good thing to have at the surface, hydrogen. Okay. We also use, there's one product in this plant we use this on. A lot of you might even know it by memory. I think Rob should know it by memory, anodic sulfuric. Yeah. You don't have to remember it, but you have to remember to look at the EDS because it hasn't been too long ago somebody didn't read it, wired it up cathodically, and we had about a half of an order with peeling gold on it. Just a little bit of peeling because it was wired up wrong. I'm not really sure myself on this one why this one works, but we just found that through experience. Okay, so for the acid, we basically have either sulfuric in there, or rare occasions hydrochloric. Sometimes we put current to it when we have something that's difficult to activate. What you're doing is you're removing the last bits of oxides left, and you're also removing this slime that's left on because of the caustic. Okay? You want to be real careful to make sure that position 15, rinse right after here, is working right. Because remember, this is a pH of 1. If you don't rinse it and blow it off and you drag it into the nickel tank, the pH of the nickel tank goes down. So pH, our nickel is sulfonate nickel. The pH of that is about 4. The pH of this is about 1. When you drag enough in there, you're going to make this pH go down. Now it's pretty flexible, but if it starts going too low, then you start having problems. Okay? So that's about it for acid activate. I think well, maybe not. I don't want to speak too soon, but pretty much every product we use in the plant gets acid activate. Strikes. Okay, we have a couple different kinds, or several different kinds of strikes. But for us to strike any plating, any strike bath we use in this plant has basically the same primary function, the primary reason why we're using it. You don't have it?
You coming off another sheet, aren't you?
Yeah.
We got this last time.
Oh, backwards. These are all turning around, mixed up. Strikes. What is the purpose of having a strike bath? There's really one reason we use it. What are we trying to do by putting a strike on the part?
Make the gold bond better. with
Yeah,
it.
well, you shouldn't say
Kinda
gold.
like a
Not
primer.
necessarily gold. It's like a primer, exactly. It's not necessarily to make the gold stick. It's to make whatever the next thing is. Yeah. But the reason we use them is this, adhesion. That's why it's in the line. Now, there might be in some rare occasions some other purpose of it, but basically that's what it's for. Okay. Like for instance, we've done before where we put a strike under a tin lead, then we put a tin lead on, and we strip back the rest of the strike, and then for solderability, we've done that before. But basically, this is what it's for. When you put a strike on for solderability, you're trying to fix some other problem. What's wrong with the solder bath or something. Okay, just a couple basic basic parameters of a strike bath is they tend to be, but not always, they don't always have to be, but they tend to be low metals, okay, low efficiency, or low efficiency, and low pH. Okay, all three of those things the strikes tend to be. Now, everyone uses this word and everyone talks about this word right here a lot. So I just want to make sure we all understand what really that means. Efficiency is the percent of the current that is being used to deposit metal. Used to plate, okay? And it's especially really important in gold plating baths, for instance. If you put 3 amps through a hard gold plating bath, probably 1 amp is being used to plate, and the other 2 is just nothing. It's just being used to make hydrogen, okay? But it's how much of the current that you're putting through that cell is going to deposit metal, okay? And these baths here are very low efficiency, which means you have a lot of hydrogen. That's why you see in a strike usually, if you turn it up at all, it'll start gassing. Okay. Also low metals, and this is they sort of go hand in hand. I mean, this same thing will happen to a hard gold bath. If you let the metals go low enough, it'll get low in efficiency too. Low pH, it's not necessarily like this, but it tends to be lower pH because it makes it acidic. It tends to make it lower in efficiency, and it also makes the bath acidic, so it's active. Okay? Now, basically we use 2 kinds of strikes. Never use a strike for a tin lead because it's almost unheard of to have a tin lead adhesion problem.
We haven't tried it.
Probably for solderability or something. Yeah. We've tried everything for solderability, but yet now we don't seem to ever have that anymore. I know, I've seen everything try to solve solderability problem. But I think that turns out to be a problem of the lack of control of the solder bath and additives. We used to really dump them in there. Okay, so we have 2 types. You got nickel, and in that we have a Watts. It's actually a modified Watts, but we'll just call it a Watts, which is a sulfate bath, okay? Which has sulfuric acid in it. Same acid that we use in the activator. Then we have a Woods, okay, which is a chloride bath, which has hydrochloric acid in it. We tend not to use this one, and it's for the same reason we don't use hydrochloric acid. We don't like this in the plant at all. But also, for stainless steels, we found, our experience is this one doesn't work as good. This is the one that works best for us for stainless steels. And stainless steels is where we use a strike, basically, more or less. I don't think we use it on anything that's a copper or that's not a steel. We use it on LTI Jenna, and we use it on amp stainless steel. And just, example, this bath here, we'll compare it. You got a Watts, and you got our plating bath as a sulfamate. Okay? Okay, the Watts, pH, like 1. Sulfamate, pH 4. Okay? The efficiency of this bath is nothing. You can't plate. You'd have to go a half a meter a minute to get 5 microinches out of a cell. But you don't care because that's not what you want. You just want something on it. Okay? Woods nickel is basically you're doing the same thing, but it's got a chloride in it. So we really don't use this except on burning, which we're not running now. Okay? The other type of strike we use, gold strike. this Gold Strike does not have a lower pH really than the Bath, okay? But it's got low metals, very low, which causes it to have low efficiency, which means you get lots of hydrogen, and not much really plating, okay? So they're very similar. They're basically for the same reason, to get something to stick to it. I want to also just mention ultrasonic cleaning because a lot of people talk about it. What ultrasonic cleaning is basically a way to get a great deal of agitation at the surface of the product. And it's usually used in a caustic cleaning solution to get rid of oils. Okay, so it just sends a sonic waves through the solution and it causes all kinds of what they call cavitation. And it's like a formation of voids within the solution. But anyway, yeah, the thing to remember is it's causing a great deal of agitation at the part, and it helps it clean very fast. You run really high line speeds with really short cells. So you say, okay, that sounds great. Why don't we use it? Well, there was a cell over in Holland. Actual length here. Okay, that's about the actual length. It's a tube. It's a round tube. Up here you've got a generator. This is a transducer. Okay? This is where your product goes through here. And this is the thing that's, this is the generator. This unit right here, this big, costs about $25,000. So, there you have it. You don't use it.
That's all that problem. As simple as that, it's down too high.
It was either that or a new truck.
That Sonoma is looking mighty sweet with that light blue.
Like it's stock rim.
They just have one of those in the line, that's it?
Yeah.
Just one?
Oh,
Yeah, they have cleaners too now.
Oh,
But what they do is, a lot of these guys, you talk to these guys, some of our customers from the bigger companies that have a lot more money, and they love it. They say it's great, but they also might be running a lot faster than we are.
Obviously.
What's the
they're
difference
cleaning
between
better.
that? Will it be cheaper to buy one of these than to buy a whole new line? Or I don't know, you know.
Yeah, but
I mean,
all that does is speed up our cleaning
Clean.
operation.
Okay.
Then you still gotta speed up your
Look
nickel
at it this
operation.
way.
Well, the reason
Go
why
out
Holland
on the
did
line,
is they run a lot faster
When you
speed,
run it
they run like a
forward,
flat stock. They don't run
Highland doesn't use it either. What I'm saying is I saw this in Nico Equipment where they were building machine for another company. I think it might have been AMP or DuPont. And those guys swear by it.
So Nico as a whole doesn't use those.
Well, I don't know about Hong Kong now or Malaysia.
Oh yeah, why do anything?
Well, you know, if you look at it and you say, okay, how many times do we go out there and say, man, we got to slow this line down because we're not cleaning it good enough?
Well, does this eliminate electric power?
No. It's not a replacement for electric polish.
But why do we?
What cleans better, that or electric power?
Well, see, the
Cleans
polish
better?
breaks down.
Well, they do different things. You
Oh,
can't
yeah.
replace
Polish
one with
breaks
the
down
other.
the copper, and
I didn't know if they did the same thing.
this just cleans the
Electropolish is removing material from the surface. But the electropolish isn't going to take the oils off this product. It's not. I mean, you wouldn't see a product come into the line, the first thing it sees is an electropolish. You would never see
I
that.
don't have a problem with the male serpent or the female serpent.
See, now the surface might be one where that would help us.
Yeah, but now we got their little space
Their
age
little,
cleaning system up there.
Super duper jet agitation.
Machinery there.
Hey.
Hell, that might be just as good, you never know.
But it's the same effect, see? We're spraying it on there, but that's what this is doing.
That's all that's doing is.
It's doing
Yeah,
it
why
on
just
micros-
spray it on there where we can spend $25,000 and get it?
I'll get a damn good one. It closed.
But it's very expensive. We would buy it though, for sure. We'd buy it if it was like, well, all our line speeds can double if we buy this thing. We think we'd have it over here so quick. But we don't ever run into that.
We have a 2-year long study.
Our lines are sized with a whole bunch of cleaning capacity. It's like there's way more cleaning capacity than everything else.
Why don't they make the line smaller, closer to the floor?
Yeah,
There's
they
one
crawl along
basic,
back.
very basic reason.
I mean,
There's a
to
basic
get
reason.
eye level with it, you know.
I know, there's a basic
Easy
reason.
to work with. Why?
Because you can't fit the stuff underneath of it. You gotta put a tank under there.
Yeah, you
gotta
gotta
put
put
a pump.
Tanks.
Matter of fact, when we were there in Holland, they were building
You
one,
could
they were lower.
you could revamp it somewhere.
Them tanks have to be wide.
Tanks are wider, so what happens is, I'll tell you, what happens when you get a tank this wide, like this, and the solution level drops 1 inch, let's say that's this much. That might be 10% of the volume. When you get one like this, and the solution drops 1 inch, that might be 25% of the volume.
Then you have to
Yeah,
really
redo
be
the
on
pumps
top
and
of it.
everything else.
Well, we saw one, and I'll tell you what they did. Here's what they're doing. They had these special low-profile pumps. They were like, instead of our pumps like this, they're like this. I don't know if they were more expensive. They had filter chambers. They had filter chambers sitting inside of the tank. They can do it. They had a lid cut. There was a hole in there. The filter chamber was sitting halfway in there and halfway out. All kinds of very unusual looking things, and it makes it not necessarily that easy for maintenance.
But
What
it's
some
technically
companies do is they put that up there, put your stuff underneath it, and then they build a grate.
like concrete.
Yeah, but what they also have is they have that, what falls down in there probably, I don't know, I haven't been there, but probably can drain somewhere. Probably have floor drains. We don't have any floor drains. There's a lot of problems here. It's,
Be nice
It's
if
tough.
everything be on wheels too, you know, all the
Yeah.
tanks and
All
stuff.
tanks, everything is loaded on
Just
small
roll them in,
wheels.
Yeah.
lock them down, pull it out,
it's-
slide another one in.
it's nice, and some of them do it. Some people ask for it. The problem is keeping those wheels where they don't
You can lock
Buy
it.
Well, and you gotta, we gotta
But-
keep a tray under ours.
become sleds.
Cause we're gonna spill
Yeah,
something, show
not
what they
raising
don't.
pipe.
Hell, yeah, we need a fan under
I think we don't
ours.
need no trays under them either.
Oh, yeah, let's just walk in the nickel.
Yeah, well, that $5 gold bath y'all back it up today, we've been in the damn sun, you know.
But the problem is, you're probably right about the nickel. We don't necessarily need them. But with something like a gold tank, the risk is too big
Yeah,
to lose it.
Let me tell you what, I've seen gold baths without fans under them get dumped.
I seen
And
one.
people scurrying around like cats.
See, people probably get fired too,
I
right?
sent one
No,
down
I
the
don't think
salt.
they would have fired Theo.
Did you? Oh.
I did the same thing.
Okay, so basically, you're doing it because you want to clean the part ultrasonically, and you want to clean the part faster. But our lines, the way they are now, there's always something that limits how fast the line can go. And I can say pretty safely, it's almost never the cleaning that limits our line speed. Almost never. You might say, well, you got that male serpent, maybe there, but that we don't
I think we
biggest-
got that
The
solved
biggest
now.
limiter of speed we've got right now is the blow off.
Right, well, for that one product.
I'm talking about cooling
Yeah.
all the stuff.
That's
A lot of
true,
times it's
that's
too
true, because those
business.
microphones just aren't, you know.
Well, we
I'm
got
talking
that
about all
one
of
in
them.
line 3 now, so we'll see how that does. The squeegee thing. They use those over in Holland.
That's like worked pretty good, I thought it was gonna tear apart.
But look at it very closely.
It
Instead of
takes a
just saying, it
lot.
does look sort of
It
hokey.
takes a lot of excess.
But look at the
off.
product
Elevates
coming
all
into
off.
it, and look at the bottom, and look at your solution beading on it. Look at it coming out, and there's nothing.
It's taking it all off.
Okay. One other thing, I want to talk about calculations. We're just going to talk about line speed and plating thickness. Okay. And it's really a simple calculation. It just takes 10 seconds to do, but I'm going to go into a little bit more depth of where that calculation came from. What does it mean?
How does it actually work?
Yeah. Everyone just takes it, multiplies it. I'm not sure we actually know what's happening there, or haven't thought about it. So I'm going to go from the very beginning here. There's obviously a lot of things that affect plating thickness, but one of them we know for sure is line speed. But why does line speed affect plating thickness? Is dwell time, or retention time, or residence time. Okay. what this term means, any one of these terms are all the same thing, is the length of time that one little section of material will stay in the plating solution. Okay? And when we say dwell time, we mean the effective length of time that the product stays in the solution. So that means you only count the time that is actually immersed in the plating solution and it can see the current from the anode. Okay? That's the only time you count. So if we had this situation, to calculate, and these are all the same thing, to calculate this, you take the length of your cell, whatever it is, and divide it by the speed. Okay? Now this has to be in meters, and this has to be in meters per minute, or inches and inches per minute, or feet per minute. But you can't mix things up. You can't measure this in feet and divide it by meters per minute. So this would be 2 meters divided by 10 meters per minute, and that's 0.2 minutes. Okay? So if you have a product going 10 meters per minute, 2 meter cell, your retention time is 0.2 minutes. Okay? Now, let's say that retention time, minutes, gives us 80 microinches. Okay? We want, let's say we want to increase the retention time or the dwell time from 0.2 to 0.25 minutes. We want to increase the amount of time that this product stays in there. If we increase the amount of time the product stays in there, we're going to increase the thickness. Yeah, you got to slow down. But let's say we did this. What effect would that have on the thickness? It will go up. Right. The thickness is what we call, the thickness is going to be proportional to the amount of time the product's in there. So if the product's in there longer, the thickness is going to be higher. It's just pretty common sense. But how do we know how much higher it's going to be? No. Because what you're going to do, it's the same thing with any one of our calculations. You're going to take your thickness 80, and you're going to multiply it by the ratio of the times. Okay, in other words, I know if I stay in here longer. Okay, let me do it a different way. If I take this 80 microinches, if I'm going to plate 80 microinches in 0.2 minutes, how many microinches per minute is that? That right there is 400 microinches per minute. Okay, if you take 80 and divide it by 0.2, okay, that's 400 microinches. That's 400 microinches a minute. No? But okay, so we're in there for 0.2 minutes, we get 80 microinches. So we're plating at a rate of 400 microinches per minute, right? Okay? Now, this rate that we're plating at depends on, the bath and the amount of current we're plating a rectifier. But we're not changing this. We're changing just the amount of time. If we slow the line down, we're still plating 400 microinches per minute. We're just staying in there for a longer time. So if you're plating 400 microinches per minute, and remember what the initial question was, what happens when we increase the time from 0.2 to 0.25 minutes? Well, if we're in there for 0.25 minutes, right, take 400 times 0.25, that equals 100 microinches. Okay? In other words, we know from 80 microinches divided by 0.2 minutes, that's 400 microinches per minute. That's how fast the plating is building up on the part. In 1 minute, you'd have 400 microinches if you stayed in here for 1 minute. Okay, so that's the speed we're plating. 400 microinches per minute times how long we're plating from 400 microliters per minute equals the total thickness. Same thing as, it'd be the same thing as driving a car. If we were driving 400 miles an hour and want to know how far you're going to go in a quarter of an hour, you take 400 miles, you take how fast you're going, like 60 miles an hour, times 1 hour, 60 miles. Same thing's happening here. Okay, so we want to know what happens when you increase from 0.2 to 0.25, and what we found out is that your thickness goes from 80 to 100. 80 to 100. What's wrong, Lewis?
What's the difference between that and then what we've always done down there? Like if you got 80 microliters and you want 100, you say 80 divided by 100 times your line speed.
Well, that's the way you want to continue to do it. All I'm trying to do is try to just go through and show you why that's true. Why is it true that when you multiply the speeds, and what it has to do with is how long that product's staying in there.
The same thing with the
And probably no one's gonna, you're never ever gonna do this again. Sometimes we need to ask the question, how long is something in there?
In the gold strip or something like that, huh?
Yeah.
I've got a sheet in the computer for all this now.
Yeah, it's very simplified, which in here you got, at the very end, you got it very simplified too, just two formulas. And that's what you're gonna use. I'm trying to go through and just explain why it's like that. Okay?
Okay, what's that?
Okay, so now,
Still says 96.
That was 100.
How long you been working for
oh, what, it's 100, but then you add the Lewis factor to it, so then you add
That knocked y'all full mark.
it just knocks off 4.
That's
It's
insane.
a good measure.
Take 4.
Okay, so then we want to know, okay, what do we have to do to the speed of the line to change the dwell time from 0.2 to 0.25 minutes? Okay, well obviously we have to slow the line down because we're going to be in there for a longer time, so the line has to go slower. Okay, so let's say we were running at 10 meters per minute. Okay? Remember, I'm going to try to think how to do this. The best thing to do is you take your speed that you're running and you multiply it by this dwell time. So one dwell time divided by another one.
8 meters a minute.
Right. Which is something you would know anyway, that the speed's going to be 8 meters per minute. But the reason for this exercise, and no one's ever going to do this, but the basic reason for this exercise is to say that what you're doing when you do that speed calculation is you're calculating how much you have to change the time by that it's staying in here.
Well, hopefully at a point some will start doing, you know, people start working with it that way.
Well, this is like what you're really doing when you use this whole dwell time concept is you're doing an intermediate step. When you do what you guys are doing, you just bypass that, which is fine. It's faster. It's just
It's
the
like,
same
it's like
accuracy.
taking a math class with a calculator.
Yeah. I mean, yeah, it'd be like if you're teaching somebody how to multiply and you give them a calculator. You teach them how to multiply, you say, okay, understand it, and then you give them a calculator and they never do it again. But at least they understand what it is. So just now, real quickly, how we actually are going to do it on the line is just as far as thickness and line speed, there's just two basic ones you need to know. Okay? Old speed divided by new speed times old thickness equals new thickness. Okay, this you will do if you know what you're going to change your line speed by, and you just want to say, okay, I'm going to change my line speed, what's going to happen to this thickness? Then you use this one. Okay? I don't know about you guys, but I can never remember which way these go anyway, which one's on
Do it
top.
wrong every time.
I always gotta do it twice.
Every time.
Every time.
But that's okay, I don't remember it either.
But it goes back and forth. Now, if you want more, you have to do it one way. If you
There
want
there
less,
are
you have to
different
switch it.
applications, but as long as you know you're looking for a lower answer.
Right.
or
But
a
you never
higher
did
There's
believe me
nothing
about
wrong
that,
with
but I
that.
can show you on the calculator that
There's
you gotta
nothing
do
wrong
it
with that
backwards.
logic. No, this will work like this every time, whether you go up or down.
I'm
It'll
telling
work
you, it
every
won't.
time.
It won't.
Okay,
though,
let's.
look.
Okay, I'm gonna show you. Okay, I'm gonna show you.
Well, the damn calculator
I'm
won't do it.
gonna
I'll
show
tell you that.
Let's say that we go from 8 meters a minute to 10 meters per minute.
On speed, yeah.
Okay.
Thicknesses is different. He's right.
I might have it. I might have it.
If you want thicknesses,
Yeah, this is
then
right.
you got it backwards, but if you're going speed, yeah, you're
This is
right.
8 meters per minute. We're going. Okay, our old speed, the speed that we had before, was 8 meters per minute. Now we speed up to 10 meters per minute. Let's say that we had 100 microinches. What's our new thickness going to be? This one I can do in my head. No, see, you already did it backwards. It's 8.
Yeah, think about it backwards.
Okay. So this is right, right?
Okay,
This is
all the
right.
time.
Yeah,
Okay.
the speed
Now,
thing's right.
now let's try
But if you
this.
go for the thicknesses, then you gotta do it 2 or 3 times.
What the thing to remember is exactly like what Lewis said. If you're gonna, if my current speed is 8, and your new speed is 10. Okay, and you say, what's gonna happen to my thickness? Well, you know you gotta divide these speeds.
You go down 20%.
Yeah, and you know you gotta take, well, 8 divided by 10 or 10 divided by 8. And if you can't remember which way it goes, then don't worry about it, really. As long as you
Do
don't,
it twice.
as long as you don't figure this all up, and you come out here, and if you do this backwards, by the way, it'll be 125.
Right.
If you get 125 and you say, okay, that's what happens. I'm going to speed my line up from 8 to 10. My thickness is going to go from 100 to 125. Then, you know, that's not too good.
That's what I'm saying. If you do it
I mean, we
backwards,
would
it
be
comes
going
up.
about 5 billion miles an hour down there if that was the case, right? So what I'm saying is, you know what the answer is supposed to be.
What I'm saying is if you go backwards with it, you come up with 125.
Right.
Okay, that would be like your speed line up to 10 instead of.
It would be like.
That's what I'm saying. When you go backward, you know, when you go like 10 divided by 8, it comes up backwards. It
No.
goes up the.
But follow this exactly the way it is and try it. Let's say, let's do it the other way.
When it comes up, yeah, it comes up by 80 microinches.
It'll be right. Let's say your old speed or your current speed is 6 and your new speed is 5. Okay? Your old speed, 6. New speed is 5. And let's say your old thickness was 50. Old thickness times old thickness, which is 50. What's that? 60. Okay, that's right, right? I followed this exactly the way it's written. I got the right answer. Because I went from 6 to 5, so I slowed down. My thickness went from 50 to 60. Okay, so this will work.
Okay, I might
There's no need to remember.
the speed, not realizing.
The most important thing to remember is if you want to know how much your thickness is going to change by a line speed, take the thickness that you've got and times it by one speed divided by the other speed. That's all you got to do. If it comes out the wrong direction, then flip them around. You'll get it right. Okay. The other one we do, this one we don't do quite so much. The one we do more frequently is we say, how much do I need to adjust the speed by to get a certain thickness? This one tells you if I adjust the speed a certain amount, what happens to my thickness. But what we do more is if we want a certain thickness, how much do we have to adjust the speed to get it? And I'll write it down so it's right. I have to copy here, and I know this one's right. Actual thickness divided by desired thickness times actual speed is desired speed. This will work every time. I don't care if you're going up, down, anything else. It'll work. You put it in exactly like this. And we'll do an example. Let's say you're running a job. You're running 80 microinches. Okay, but you want 60 microinches. Okay, 80 is your actual divided by what you want, which is 60 microinches, right? Okay. And let's say your actual line speed is 6. Okay. That's going to be 8. Okay. In other words, if you take the actual thickness, I'm going to write this out here. Desired and the actual speed is 6. So if Lewis, if you were doing this, you would take 6 and you'd multiply it times one of these divided by the other one. And if you take 6 times 60 divided by 80, you'll get, I don't know, 45 or something. Or you'll get 4.5, I mean. And you'll say, well, I want to go from 80 to 60. My speed's going to go from 6 to 4.5. No, that's wrong.
That would be my first one.
Yeah. Your first one.
And then I'd go back through it and get it right.
But just the thing to remember, if you want to know what your thickness is going to be when you change the speed, okay, take the thickness that you got and times it by, divide the two line speeds by each other, okay? If you want to know how much your thickness is going to change if you change the line speed, take the thickness that you got and times it by divide the speeds by each other. So if you have 50 microinches and you go in 6 meters per minute, and you want, let's say you want 75 microinches. You have 50, you want 75. First of all, what do you have to do? First you think, I gotta slow down, right? So you know you gotta be slower. Okay, you want to know what the new speed is, so you take the speed that you got and you times it by these two things divided by each other. And you know you have to slow down, which means you're always going to divide the bigger number into the littler number. But even if you can't remember that, that's okay. Because if you get it backwards, it will come out with a nonsense answer. And that'll be 4. So, if you got 50 microinches, going to 6 meters per minute, you want to increase to 75 microinches, you got to go down to 4 meters per minute. And it's important that we know how to calculate instead of just knowing we have to slow down, walking out there. I'm just going to slow it down a little bit.
I would have calculated.
But there's a lot more to calculating, and it can get real
There's
tricky.
a lot more of just that right there. Let's say you're running 80 microinches, you got your spec on nickel and tin lead.
Yeah.
You want to increase your amps on the gold and increase your line speed to keep your nickel and tin lead where they are.
Right.
So now.
Well, yeah, and what happens if I present you with a case where I say, here's your specs, you got nickel, gold, and tin lead. Here's your specs, and here's what you've got. And let's say this one's 50, 30, and 100. And here you've got 78, and here you've got 46, and here you've got 142.
You want the line speed or?
Yeah, I want you. First of all, I want you to tell me, and we don't have to go through all this now, but this is an example of something we can get into. I want you to tell me which one of these things.
First of all, you go through each of them and you figure out your line speed, find the lowest one,
Yeah.
multiply that by the line speed.
What is line speed, by the way?
Yeah, let's say the line speed is 5.
You're going to figure out what each of them drop to, then calculate it down to your
Yeah.
spec.
And you've said a lot, and I'm sure you're right, but the point is there's a lot to this, because you have to say, okay, which one of these is limiting? Which one? Because you can't really tell by looking at it.
None of them, yeah.
78.
Nah. I'd say you could move line speed and about all that with everything.
Well, I'll tell you right now which one limits it by looking at it. This one does. But you might not know that.
But I mean, I guarantee you could do line speed, bring every one of those in spec. I mean, not dead on it, dead on it, you know
But
what
what
I'm saying?
happens if this one is, what happens if this one's 83, okay? And let's say, okay, I gotta bring my nickel down to 55. I say I got an 83, so I'm gonna speed up to bring it down to 55. You gotta know if that's gonna go low.
Right. Right.
You gotta know which is the one that's limiting.
You got to
And we'll go
calculate
through
it.
that, but not, I mean, it's a really involved thing. It's really involved.
Did it all day the other day when we was putting that shit up.
That's it, though, we're finished.
Good.
Well, sorry about the pizza, fellas. I'll make it up to you somehow or another. Mike Robinson, I'll let y'all detail out of it. All right, get out of apple fritters.
Hey,
Hey.
hey guys, Lewis, could you, why don't you carry this down there? Joe Burns will eat them all. Just set it down. That's what those guys said. They said they'll just eat them one at a time so they're all gone.
I'm just gonna take it straight from
There's probably several people in here that remember this. Down inside that wire barrel, on the inside of it, is very low current density area. It's hard for the current to get down in there. So you run this product through a cleaner, and you get this problem where it's peeling right inside that wire barrel. If you looked at it from the front, this is the greatest drawer. If you're looking at it, you're looking down into the wire barrel, right down in here, you get these peeling or bare spots, because there's almost no current density down there, so you don't have any gassing, you have a poor cleaning. That's why you see at the front of lines, and I think it's only on lines 3 and 4 now, because that's the only place you run these kind of products, you see that jet thing, which is that, it's like a stainless steel tube, and it's got some jet nozzles like this sticking out of it. And those need to be directed right at this area. And you blast that area with cleaning solution, and that gives you your agitation and gets that cleaned out. There's a couple of them. There's a DuPont Serpent, male Serpent, and another one is Wire Pro that we use that on. We had another one also, Wakanda, the Wakanda pin. Okay. Just want to make a couple more notes about this cathodic cleaning. The air wipe. You got your cleaner cell here, and it's got and here's your solution, and then right here you have an air wipe. That should always be on, always. If you're using this should be on. And I know years ago we had this thing where we said, well, if the effluent, which is the stream going out of the plant, if the pH is low, we'll turn this air wipe off. We'll let some of this caustic cleaner, which has a high pH, we'll let it drag out. It'll neutralize it, and then we won't have a pH problem. Well, there's no control with that. That's totally, don't do it. Just always leave this air wipe on. It keeps the cleaner in the tank, and we don't have to add so much chemicals back to the tank to replenish it. I think everybody knows this solution to backfill, just use city water. Also, one other thing is the rinse. It comes out of here, and you got another little box here. You got a rinse. You got an air wipe, right? Something like that. Please make sure that rinse is working, especially if you're going into electro polish. either if you're going into electropolish or if this is position 12 and you're going into an acid here, remember this is a caustic, this is an acid. And the more of that you drag into here, you're going to neutralize this. And we know some of that's going to happen because if any of you have gotten this, and I'm sure you all have, any of you have got this cleaner that's from position 5 or 12 on your hand and try to just turn the water on and go like that, like we do to our parts, and feel if it's still on there. You have to rinse it good to get the soap off. So that's why we need a lot of water. Also, that's partly what's happening here with 14. If you have that stuff on your hands and you go over and try to rinse it off and it just takes so much water to get it off, and don't do this, but if you were to put your hand in the sulfuric acid there, it'd be gone. And that's partly what you're doing there. It's very difficult to rinse off soap film. Okay. Electropolish is the next cleaning operation. Electropolish, basically what you're doing is electropolish is always anodic. The part is always anodic. Okay. Now I'm gonna simplify this a little bit from what we have out there, because we have that setup out there with the dummy plate section in the beginning of the electropolish cell, which all the lines it's jumped out, I think, because all the anodes are not working. So this is how it's really, this is how this thing is really working. Okay, and then we have a rectifier here, a rectifier here. Okay. Put the positive. And here what we're doing, either directly or indirectly, sometimes this wire goes to here and then somebody just connected a wire over to here. So it's the same thing, it's just having it. These are both hooked to here. And this negative is hooked to there. And this positive is hooked over to here. Right? Do I have it right?
Yeah.
Okay. And there's your product going through. So what we do is we get the current flowing through both cells without using any contacts, which is that's kind of a nice feature when you have a product that's difficult to contact. Basically what we're doing is this part in here is an anode. The same way a nickel basket is an anode in a nickel solution, or a tin lead basket or a tin lead bar is an anode in a tin lead plating solution. So your part is dissolving into this solution. It's also plating out here. And what you're basically trying to do is, if a product is real difficult to clean, or it's got a heavy oxide layer or something, you're just taking a layer of that material, just taking it right off in this polish cell. Remember that if we wanted to calculate, well, how much current are we running through the polish cell, add these two together, is all the current's going through there. Basically what's happening, it comes out of here, it goes to this plate, it jumps across here. The whole, when you're plating with direct current, or when you're using direct current, that current, all it wants to do is it wants to, as hard as it can, it wants to get from here to here. It's like having a ball up on the top of a hill and let it go. It just wants to get to the bottom of the hill. That's all it's doing. So it keeps going down here, it goes across here, then it goes here. Okay, so here you're dissolving off, here you're plating on, then you go up here, and it can go to either one of these. It doesn't really matter. Okay. And the same thing here. Comes around here, comes across. Boom. So that's the way your current's flowing. And here, whenever that current leaves the metal and enters into the solution, that's where you have your things going on. That's what electroplating is. Here, oxygen, right? Because there's no metals in this bath. at all. Here you have hydrogen. Gassing. Here, you also have oxygen here. But you're also dissolving some copper in here. Here you're plating out some copper, and you've got some hydrogen gas. Okay? And here, again, you've got hydrogen and oxygen here. But these two guys, they're just doing the same cathodic cleaning that you would have if you had a contact right here.
Sludge that builds up in there, is that, the copper?
That's the copper from the part. It's dissolving very slowly, but you pass enough product through there, it's coming off there. And it's the same thing as if, usually, in almost every other station in the line except this one is wired the other way. So our stuff is always plating out onto the part, which is going away, and so we don't really see how much material we're depositing. But this shows you you're depositing material and keep continually depositing it. And it's coming from this part. So if you ever see you're running the polish and there's nothing on here, check your wiring, because you're probably backwards. It should be copper, should be building up on it. Since it does build up, and sometimes it'll build up pretty quickly. It depends basically directly on how much current you're using. The more current you use, the faster that copper will build up. So you need to every once in a while get in there with a vacuum cleaner and clean it out. There is a way of estimating, well, you say, okay, you got a big runner. How long should I run before I vacuum it out? Because, you know, a lot of times our runs are so short, it doesn't matter. You just vacuum it out in between, or you shut down for something, you vacuum out. But we have a way of estimating it, okay? We can run about 1,800 amp hours through the electropolish cell before we have to clean the copper out. Now, an amp hour, 1 amp hour would be if I ran 1 amp total through the cell for 1 hour. That would be 1 amp hour. If I run 1 amp for 2 hours, that's 2 amp hours. If I run 2 amps for 1 hour, that's 2 amp hour. You just multiply them together, that's all it is. So all I'm saying is, let's say we ran 20 here and 20 here. All 40 of it is going through here, right? Okay, so let's say this is what we're running. You were there running your line, you're saying, well, I just cleaned it out. I wonder how long I can run before I have to clean it out again. Estimate, okay? Total amperage is 40 amps, total, that's running through this cell. So how many hours can we run that before we reach 1,800 amp hours? Whatever this is divided into this. Okay, because you take, let's say I run this 40 amps just like it's written here, and we run that for, let's say, for 5 hours. How many amp hours have we run? 40 amps, 5 hours. It's 200. It's just simple. That's all it is. You just multiply them together. So 5 hours you would have 200. So it's 9 times as much. But all you have to do is take that 40 amps, your total amperage, and divide it into 1,800. So if we were running 30 here, and 30 here, you take 1,800 divided by 60, because the 60 is the total current you're running through there. That would be 30. It says you can run for 30 hours. Now I think if you think about it, like on Maju, this is probably, maybe we run higher than that. Do we run high on the Maju raw? And so that says 30, you can go 30 hours. I don't think we go 30 hours. So are we vacuuming out every time we take the contacts out? How much is in there? Is it bad? A lot?
It gets a lot in there.
Yeah, so this might even be a little bit off.
Of course, we
Maybe
do
we scrape that stuff off.
do it like that. Yeah, it's easy.
12 hours? is,
I thought we just put them on the floor and mop
see,
it
this
around
is
and then
basically
go off.
saying you can't go any longer than this. This is saying that, you know, not necessarily you have to wait this long, but right, don't wait any longer than that. And if you're running 80 amps a cell, it's going to build up fast. It's going to build up real fast. Okay. One thing I don't know if everybody knows about the electropolish solution is we can't get any water in it. We don't want any water in that solution. It's the only solution we have in the plant that's like that. And it won't. The action of the electropolish, which is to evenly, smoothly take off a layer of copper, won't work right if we start getting a lot of water in there. That's why you look in here, we have this position in here with the 3 air wipes in position number 7. We have triple air wipes there. Plus we have, in 6, we have an air wipe here too, right? So we have 4 air wipes in a row. And a lot of times these things don't get much attention. But if you just spray them down with a little water, there's a drain down here. You don't have to vacuum it out or anything. Just spray them down so they stay clear. Then we keep the water out of the electropolish. And that'll make it. This polish solution, by the way, to make up 1 bath, about $2,000 worth of chemicals. Okay, just the chemicals that go into making it. It's real expensive. And you notice we don't change them a lot. We haven't changed one probably in a year. I can't remember changing them. That's the way we like to keep them. Another thing, the electropolish, the best operating temperature of electropolish is about 20 degrees C. And when you start pumping all this current through there, and you got a big pump down in the tank and swirling stuff around, the temperature will heat up. So it's got a chiller in it. And anybody that doesn't know, there's a compressor down here that chills this little tank of water. There's a tank of water in here. That compressor chills that water. Then there's a pump that pumps that chilled water down into this thing to keep it cool. And up here, there's a panel up here. And it's got a thermostat. It should be set on 20. We should be checking that to make sure that something doesn't go wrong, because this thing here has a tendency to sort of not work all the time. Okay, numbers. After we get out of this electropolish station, in between here, 2 positions, there's 3 in between here, but 9 and 10 are the dragouts. Okay, these need to be working right. We have a problem in this plant with copper in the effluent. We're not far out, we're not out that often, but we have occasions where we're going above the allowable limit of copper, which is something like, I don't know what it is, but it's, you know, on approximately 1 or 2 parts per million you're allowed. So you allow almost nothing. And when this doesn't work right, when 9 doesn't work right, when 10 doesn't work right, 11 rinses, and the rinse from 11 goes down the drain, out to the city. So when these things aren't on or they're all clogged up. Another thing is position 9 is just, well, actually both of these you all don't really need to worry about as far as the stuff in the tanks. Just let the lab take care of that. If there's a problem, then tell them. Because there's position 9 is made up with electropolish solution. That's so they can take it and backfill it back in, so we try to keep the copper out from getting out of the plant. So just, that applies also to position 8. Position 8, 9, and 10. Down in the tanks, don't worry about it. If there's something low, something's not acting right, then tell somebody in the laboratory. But up here on top, to make sure that things aren't all clogged up or turned off or whatever, that's something you can worry about. The other reason why we need to keep those working is, and the perfect example is the Maju Raw on line 3, and probably everybody's run that. And we see what happens, even when they're working right, you see what happens in position 12 after about couple hours or something. It's all blue, just because this stuff is just dragged through here, it's dragged all the way through here, and boom, it's in there. Now we have copper in there. And none of us really knows how much it can take. We know it can take some, because it gets blue right away. We don't really know how much. The other day we found out that there was a limit to it, because we had peeling. They come in and change this out. And that's really a bad way to go about doing it, is wait till you have some defects and then change your cleaning. That's what we did. But the point I'm trying to make is it seems like those two positions, out of everything in the line, maybe almost, is the least watched. It just, it doesn't seem to matter very much if it's working or not. But that copper going out of the plant is high. It's high consistently close to the edge of what we're allowed. Now we've got this, so everybody knows we've got this blower thing, but that's off. It's on, but it's off in the future. Where we're going to add a big, enormous blower out on the side of the plant and we're going to triple our pressure to our air wipes. And we're hoping that's going to solve, that's basically for this problem. This problem and the problem of lead at the other end of the line, where we can't use the drag outs because of the tin lead backstrip. Okay. I think, let's see. I think that's it. We'll just quit there. If anyone has any questions, we'll just stop there at the end of the lecture. Part number. So we just tack on this number on the end of it. So you'll have, if you type this in to the computer, you'll have EDS 028 -1.1 -1.2 -1.3 -2.1 -2.2 -2.3. So if you're running on line 2 and you're looking for the instruction for the second pass, you get this one, right? -2 means line 2. This 2 here means the second pass. Okay? But the key to remember is when you go to look for one, just save yourself some time and just type it in like this. You'll never go wrong if you type it in like that. What it does is it'll just flash up at you every one you have to pick from. Sometimes there's only one, which is great, and you don't have to worry about it. Okay, so we want to talk about feedback. Again, I already made the point earlier talking about something else, but I want to re-emphasize. Please let us know. Not telling us, but writing it down. If you see something wrong, or if you see something you think can be improved on in the process. Take your sheet with the written change or the written suggestion or whatever it is, put it in the basket on top of the file cabinet in engineering. It says return EDS is here or something like that. Okay? It's important. A lot of people come up to me and says, this has been wrong. This was wrong last time. Now I get the EDS. It's still wrong. Why haven't you changed it? And my answer is, why didn't you write it down and tell me? Because I can't remember everything. Please tell me. I'm going to talk about sample sheets. First of all, I'll talk about how they came to where we came to use them. Lewis, Rob, Scott, you remember the setups and startups that these guys have no concept of. Startups that would last for not shifts, but weeks. Weeks without running any product on the line. And it was a while ago we said, we would be the 4th or the 5th, the 6th day into it. And Mr. Ingram would come down and say, well, what have you tried so far? And we would sort of, well, I think and no one, it was very difficult to remember when you start getting really deep into exactly everything you've done. So we said, okay, stop if you're going to try something, if you're going to try to run a sample, you're going to document. You're going to make a sample sheet. You're going to get QC results for it. You're going to staple it together. You're going to keep it together. So we have some tracking of what we've done so we don't retrace our footsteps and do the same things over and over again. That's the way it initially got started. We have, thank God, gotten away from the 9-day and 10-day setups, startups. So that's really not so much of a problem. The important part of the sample sheet is one. It keeps your sample that you ran with the product and the QC results together. If you staple them together, then you know. And if you write sample 2 on your sample sheet and you put sample 2 on your sample, then the QC can put your results with your sheet, and when you come walking in there and look for your results, you can say, well, I know this is the results from the sample I just ran, not from some other sample, because here's my sheet I just brought in and they're stapled together. That's one thing. Another thing is shift change. Especially when we change shifts and a line is not running. And this is something we are not very good at. That, if you pass on an accurate sample sheet of the last thing you have done, that gives the next operator, at least he's starting where you left off and he doesn't have to just start all over again. So it's a key. Plus it just helps you organize your thoughts. If you go and say, I'm going to carry a sample here, I'm going to carry a sample sheet in here with you. It makes you think, makes you stop and think, what did I do exactly? What currents, everything did I run? And so you'll organize here what you've been changing, what you've been modifying. The key point I want to make about sample sheets, and this is one of the most important things to me to make, because it's a sort of a sore spot for me, is the sample sheet is not a process document. Okay? A lot of people come up to me and say, well, the EDS says run 20 amps per cell, but I pulled out the last sample sheet we ran, it says run 12 amps per cell. Please go by the EDS. If it turns out that in fact the EDS is wrong, let us know, we'll change it. But the sample sheet engineering has no control over it. It can be any person at all in this plant can change that, and it can be done by anybody. So we can't say anything about the accuracy of that information. Okay? Now it could be that the EDS runs wrong, but if it is, and if you let us know, it'll be changed, it'll be right, and no one can change it. And none of you, if any one of you go in there and try to type something onto an EDS, it'll let you type, but if you try to save it, it'll just beep at you and give you a message you cannot save it. So you can't save any change. That way you know it's in control, it's under engineering control. Please do not use a sample sheet for a process document that tells you how to run. Okay? We'll talk a little bit about what time?
8:05.
7 after 8.
Okay. Just a few more minutes and then Tim will be here. So talk a little bit about using the computer. Okay, and I've already decided that I think we're going to have a separate session where we can all stand around a computer. It's very difficult. I found out in the very first class trying to walk through all these steps without having a computer, but we'll go through just the basics. To look for an EDS, we're going to run through it. We're going to talk about it a little bit, but to actually do it on the computer. You walk up to the computer. Let's say we already talked about how to get your number and everything, and about how to get your EDS number, how you get the part number off the production schedule. Walk up to the computer and say, okay, I want to get an EDS out of here. First thing is, I'm going to assume that the computer is showing the main menu. If it isn't, find somebody like me that can get it to the main menu. Somebody can do that. You've got the main menu. This is what you do. It's very simple. Type W for write. That's basically telling the computer you're getting ready to use the word processor. Okay? Type G. I was waiting. I knew you. G, forget. You're telling you're telling the computer, go get a file for me. Go get it. Then as soon as you type that, it says, it's going to ask you a question, what file number do you want me to get? And it's going to flash up something that looks like this. Got that wrong. Okay? It'll come up looking like that. You have to type in this slash like this, EDS, another slash, and then type your file name. Type your file name the way we talked about it. Type EDS, the number without the letter from the thing, XXX, and then what?
Asterisk.
There we go, asterisk, dot, asterisk. Everybody remember that. Okay? Then, boom, it'll come up. Well, what it'll do is it'll list all these file names for you. Then you just go down and pick the one you want, hit return, it'll come up on the screen, okay? Comes up on the screen, depends what you want to do. Sometimes you may want to just, you may say, well, getting ready to start up AMP Bandolier pin 1046, whatever it is, 104660-3, what size paper do I need? That's all I want to know. Just punch it up. Don't print it. Just move. Just use the arrow keys. Move around. Down there at the bottom, it'll tell you use 5/8 paper, whatever it is. Then you're done. If you're done, escape twice. If you want to print it before you escape, press F2 and then F10. Right, then it prints it out on the printer over by Scott's desk. And you got it. The sample sheets, again, it's very similar. You go to the computer, you type write, you type get. The only thing is this time it has to look like this. And then you type form, and again, type the number from the sheet, the same number from the product listing, and again type the asterisks. Okay. But let's say you go, you want to pull up an EDS, you type write, you type get, and when you do it, you see this. Let's say you see this. This is wrong here. You won't find any EDSs if you have this word right here, data. It has to be exactly like this to find the EDS. Write, EDS, and then out here you put your file name. If it doesn't look exactly like this, you have to go and just type it in. Just move it around, use the arrows, move the thing around and type this exactly in, then type your EDS name. It will come up. Okay? And if there's questions about that, just find me. I think Lewis is very familiar with it and how to use it. And a lot of other guys are, but it's something that's important to know how to do. And I think every operator should know how to pull from EDS on the computer. Time should be about right. Is there any questions? Are there any questions? Nothing. Okay. Then Tim's going to talk a little bit about production paperwork, about the production sheets and tickets and stuff like that. But in the meantime, check over and see if we got some points here. Okay. I'm just making sure we cover all this. Plus my back is killing me.
Why are you filming this, Doug? Am I sending it in the America's
Why fun? Actually, this is Jack's idea, which I think is a good idea. The reason, I don't know if Ron would want me to do this or not, but I think a lot of people don't know what the structure of this company even is. And it's something that's,
I
always-
don't. Yeah, it's gonna bother you right now.
I'm gonna do what?
Sure you got that in the right position.
I'm gonna do what?
Showboat.
Well, I just think it's important. Everybody knows. Who works for whom? And this is, and you got Tim, production. Okay. And then over here is, Tim, this is because you're late, by the way.
Oh,
Under Tim,
Got stuck all over.
under Tim, you got all you guys. You got all the operators. You got maintenance. Okay, and you got hazardous waste. That should be right. Here you got shipping. Right, Donna. Scheduling, which is Daniel. Okay. Here you got Alan. You got David Mouche. Does everybody know who David Mouche is? No.
Rob don't.
Rob, who is that?
Well, that's that guy.
You gotta keep
David
that
Mouche,
in the line
and
running.
you've got Jim Young in the lab. Okay. Oh, also one other thing over here, Jim Bailey. He's sort of just his own little world. And then here you've got obviously all the QC people and Scott Heatherly. Okay, and all the QC people.
I think you got that right.
Tim must have been absent that day. They got stuck.
That's correct now. Although this Scott's being looked at, as far as, but it'll be a little different.
Oh, Scott and Kevin, yeah.
It'll be more side by side, but that's filler. Now Tim is going to step forward, take control, tell you all about production data or something.
Well, one thing about it, we won't be able to tape him because we got 2 minutes of tape left.
That's all right. We already got him 3 times.
Yeah.
You know showboat anyway.
Tim don't get to draw.
Man, this is my last time I was gonna do this. I was really gonna do it good.
So you got it right first 5.
Oh well.
Get that?
All right. Now we're going to talk about production documentation. And I'm sure you've all seen the little cartoon of the guy sitting on the pot, toilet paper, and it says, "Job is not over until the paperwork is complete." He's wiping his butt. It's the same way with a plating line. Somehow, some way that relates to it. But no, what I want to do is talk a little bit about the production documentation. The two pages I have that I just gave passed out are examples of the things we're going to talk about here. The IOE sheet, as it's called, the line check on the back, and a blown up copy of a MECO real tag. Now, the last 2 pages in your book, before you put these other ones in there, were talking basically about the accuracy and the importance and the different responsibilities that you all have as operators to fill these sheets out. Some of the reasons why we need these, it's not just for internal information and reports and all that, but we also send this information to Holland. We use it for doing quotes, we use it for doing precious metal consumptions, all these different things. And yields and scrap, and that's why it's very important to do these right. Now, again, you guys can read this over it whenever you get a chance. It just basically tells you some of the things and reasons why. I want to point out that I get to work with Donna McCall daily because the sheets are so screwed up. And some of the mistakes are truly amazing to me. Like, I don't understand how somebody can be on a line all day long. Like, let's say they're on line 3. They turn in a sheet that says line 3. What line were they on? I mean, really. I mean, you got to pay attention to those kind of details. Or if y'all don't know what shift you're on now, then we really got a problem. But I see people turning in shifts that they're on C shift and they're put A or D or whatever. And I think some of them are just, they take a sheet or something from someone else and they start filling it out, not even looking to see what's on there already. So I'm asking y'all to look at it, double check it, make sure it's right. Now the last page, what we're going to do is just kind of go through a listing of some of the things that you will be responsible for filling out. And I have been pretty lax on whether these are done right, but now that I have everyone and I can look y'all in the eyes and I can say, okay, we've talked about this over and over again, you know what you're responsible for. Now I can start getting with everyone and going over it and making sure they're doing it right, along with Lewis, who's going to be checking them, and his signature is going to be on them too. So it's as if he didn't have a bad enough reputation. It's going to get worse the more mistakes that you have on these sheets. If you look at the sheet, you know what we have is pretty self-explanatory, but just to go through it, your date, the machine you're on, the shift that you're on, your name, initials, the IOE number, the customer. Some of this information is already filled out if you're starting a new order and you take the shift off the stack of material. Then you skip over to the next thing and you see the boxes for what are you actually doing on the line. Are you in production? Are you doing rework? Are you doing stripping? Are you on the first pass or the second pass? And as a general rule, even if you are on the same IOE, if you are going over to another operation, let's say from first to second pass, or you're doing rework, just go ahead and start a new sheet. Don't even try to put a bunch of information on here. Because remember, somebody is taking these and trying to understand what you did. And the more jumbled up things, the harder it is, and then they can't do their job, and we have major problems, or I do, because then I got to deal with Don McCall. So moving onward, then you have the part name and the part number, the time the job was completed, and if you don't complete it, you continue it, you put continue to the next shift. Your scrap weight, once you weigh your scrap up, and then it's going to be signed by the supervisor. And then down here, again, all this information is critical. For every reel, you need to fill out the reel number, the quantity, the time it started, the speeds, etc. And writing down your testing, your meters, and switching it over to your losses. All these things here are important. And then this is another area that I see a lot of people that are not really filling out, and that's this remark section. If you're running samples, please put down there why. If you run 20 samples and there's nothing over here, then we look at them and we go, what happened?
So we run a bad sample, go into QC and find out what's the matter with it and write it down here?
Yeah.
Is that what you're saying?
Just write down,
Every
yeah.
time.
You know, like, and you don't have to go into every detail of the whole job, whole sample, but just basically, was the tinlet covering gold,
Just a change made, or you want
solderability? No, just comments. Just like, why are you running another sample? You know what I'm saying?
Gold color.
Gold color,
I
tinlet
always
color.
put down what change I made.
Well, that's fine too. I mean, you could. The more information, the better. But I don't want you to.
Go back and try the same thing.
Yeah, I just, I don't want a book here, but just some general notes. And then the other thing too, if you make if the lab makes additions, go ahead and put those on there. Looking at some of the other things. If you have a power outage, what time did it happen? What time did you shut the line down? What time did you start the line up? Any mechanical failures or problems should go on there. Just basically a history of what happened during that run is what we need. And this is for traceability also. We need to come back and look at a reel and see what happened. If a customer returns parts or something, we need to look it up. We need to be able to get information. Now, the next section